This video will discuss the particle in a ring quantum mechanical model system. So to start off, we're going to define our particular model here. So we're going to have a particle, and this particle is going to be constrained such that it is free to move anywhere within this particular circle in three-dimensional space. So we could define this in the following way. So I have my x, y, and z axes, and in polar coordinates, I would measure these things as r, theta, and phi in terms of the three coordinates that are analogous to x, y, and z from Cartesian coordinates. So since we're at a fixed distance from the origin always, it makes a lot of sense for us to use a wave function which is in spherical coordinates, spherical polar coordinates. So just as in all quantum mechanical model systems, we're going to be solving the Schrodinger equation eventually. H psi equals E psi. So in this case, since we're in spherical polar coordinates, psi is a function of r, theta, and phi. R, the distance from the origin, theta, the angle that our vector makes with the z-axis, and phi, the angle that our projection into the xy plane makes with the positive x-axis. Okay, so to solve any Hamiltonian, the first thing we need to do is specify what is, to solve any Schrodinger equation, we need to specify what is our Hamiltonian. So our Hamiltonian operator here is going to be the kinetic energy operator plus the potential energy operator, as always. So the potential energy operator is just to multiply times the potential energy that our particle experiences as a function of our coordinates, so v of r, theta, and phi. And our kinetic energy, as always, for a single particle in 3 dimensions, will be minus h bar squared, Planck's constant, over 2 pi squared, divided by 2 times the mass of the particle, times the del squared operator, which we discuss more in detail below, but is the same del squared operator as always. Okay, so what is the potential that this particle is going to feel? Well, we want it to be free to move anywhere within the circle, and we want it to be forbidden from going outside the circle. So one way we can do that is we can set the potential energy to 0 if our particle's radius is equal to big R, and if the polar angle theta is equal to pi over 2 or 90 degrees. So when theta equals 2, we know we're in the xy plane. And when r equals big R, a fixed value, we know we're in a circle of radius big R. So these two constraints will give us a particle which is 0 potential energy inside the circle, and making it infinity otherwise means the particle is not able to go outside the circle. Okay, so we have our three-dimensional wave function here, psi of r, theta, and phi. But it's really not three-dimensional because there's really only one degree of freedom that our particle has. It has a fixed value of r and it has a fixed value of theta, whereas phi is free to be any value from 0 to 360 degrees around the circle. So if r is not equal to big R and theta is not equal to 2 pi, then our wave function is going to be 0 because our particle can't be outside of this circle where the potential energy is going to be infinite. So our psi of big R pi over 2 phi is really just a psi of phi. We really just have one free dimension that our particle is free to travel in. So in this case, we can look further at this del squared operator. So the del squared without any further restrictions would be 1 over r squared ddr times the quantity r squared ddr plus 1 over r squared sine theta dd theta quantity sine theta dd theta plus 1 over r squared sine theta d squared d phi squared. So since r is fixed, the derivative with respect to r is always going to be 0 because r can't change. So this term goes away. Theta is going to be fixed as well at pi over 2. So the derivatives with respect to theta are going to be 0 because theta is always a constant. And then our last term is what's going to stay here. So our value of r equals big R, which we're defining as the radius of our circle, our ring that our particle is trapped inside. And the sine of theta is going to be the sine of pi over 2, which the sine of 90 degrees is equal to 1. So this is 1, and this is big R squared. So del squared under these conditions is going to reduce to 1 over big R squared d squared d phi squared. And notice that I've changed that partial second derivative to an ordinary total second derivative, because now, since we only have a function of one variable, this becomes an ordinary derivative. So now our Schrodinger equation becomes h psi of phi equals e psi of phi, where our Hamiltonian is equal to minus h bar squared over 2m times r squared times the second derivative of the wave function with respect to phi. So this is the Hamiltonian that we'll be using in subsequent videos to eventually solve for the wave functions and energies of the particle in a ring model system.